Okay, what we're doing is working through the last couple things about gases. The first thing we're going to talk about in this video is we're going to get into gas stoichiometry. This is stuff we already know. This is our Reese's peanut butter cup situation here. We know how to do ideal gas law and we know how to do stoichiometry. So what we're going to be able to do is do the two things in the same problem. We have to be able to deal with reactions that involve gases, and what we're going to do is we're going to combine doing the stoichiometry with running the ideal gas law. Okay. The key thing here is to remember you already know how to do these things. There's always going to be two steps. One is going to be doing the reaction stoichiometry, and one of them is going to be doing the ideal gas law. And you need to remember to do them in the right order. Okay. But the problem tells you what order to do them in. So we're just going to work some problems and figure this out. Okay. Here's example one. Sodium peroxide is used to remove CO2 and add oxygen to the air supply in spacecrafts. How many liters of CO2 can be removed by 1.000 kilograms of sodium peroxide at 1.25 Celsius and 850 millimeters of mercury? All right, and I've given us the equation, so that's good. Now, we want to figure out what we have to do first in this scenario. The answer is going to be liters of CO2. Okay, this is a gas thing, and we were given sodium peroxide, which is a solid. Okay, so the first thing we have to do is stoichiometry. Okay, and our goal is we want to figure out how many moles of gas, in this case CO2, that we're looking for. Okay, that's what we're asking ourselves. We're doing the stoichiometry to figure that out. Okay, that means our starting point is our kilograms of sodium peroxide. So 1.000 kilograms Na2O2. Okay, remember that 1 kilogram is 1,000 grams. Remember that I should have put the molar mass up here, but I didn't, but I've got it for you, 77.98 grams of Na2O2. If it's not given, you can always add those up from the periodic table, but you shouldn't have to. Okay, this is 1 mole of Na2O2. Once we have that, our equation is telling us we have 2 moles of Na2O2 for every 2 moles of CO2. Okay, this is where we're going to stop because we're looking for moles of CO2. Okay, and when we multiply all this through, we get 12.8238 moles of CO2. This is a 2. Okay, and because of all those zeros, we want 4 significant figures, so that's this 2 right here. Okay. Now, since we did stoichiometry first, we're doing ideal gas law second. The second thing we're going to do is PV equals nRT, and this is where we're going to find our answer. This is liters of CO2. And this is going to be, everything in here is a gas, so we can do it. Okay, we're going to take PV equals nRT and solve it for volume since we're looking for liters. Okay, so volume equals nRT over P. Okay, we want to look at our data and see if we have to convert anything. I should have put our R's over here too, but we have that table available to us as we do that. The only thing we need to convert here is the Celsius, right? 1.25, this is going to be our temperature. Celsius plus 273.15 is 274.40 Kelvin. Okay, remember those temperature equations are given to you, so you don't have to stress about trying to remember them. Let's see, the N here, the moles, is what we were calculating from the first part. That's 12.8238 moles. R is a gas law constant. Since we're using millimeters of mercury, that means we want 62.37 liters per millimeter of mercury, oops, over kelvins and moles. And our temperature we just figured out, 274.40 Kelvin. All of that is divided by the pressure. Oh, there it is, 800. I was like, shoot, did I not give us the pressure? I did, it's right there. Millimeters of mercury, okay? All of our units will cancel out to give us liters. This should be 258.2009 liters. And if we give that three significant figures because of our, no, four significant figures because of our CO2, then we're good. 258.2 liters of CO2. Okay. All right, I don't think that's too terrible, right? Things we already know how to do. Okay. Let's look at this example. This is a fun, I don't know if a fun example is the right word for it, but it's an example um, of a great inorganic compound, nickel carbonyl. I put a link up here to a podcast I found when I was looking for pictures and extra information and stuff. I don't know if you're interested, but there we go. Anyway, we're looking for how many, let's see, what do we got? 5.66 liter reaction containers filled with pure CO at 43 degrees Celsius and 23.73 bar. Remember, this is pressure. Okay. Let's see, how many grams of nickel are needed to completely react with this CO? Okay. So this is, the answer is going to be grams of nickel. So our answer is solid. So this means we have to do the gas law first because we're given gas information and we're trying to get to a solid answer. So this is going to be doing the PV equals nRT first. So that's our first step. Okay. And what we're looking for here is moles of carbon monoxide because we were given liters, Celsius, and bar. We'll know what R is, and we're looking to convert that in the equation. So we need to have, in using the chemical equation, so we need to have moles. Okay. Let's look and see what we have to convert data-wise. Our temperature needs to be Kelvin, so 43 only 43 C plus 273.15 is 316.15 Kelvin. This will have three significant figures for us. We don't have an R in bars, so we need to get our bars straightened out. I'm going to go to atmospheres, so you can convert that to whatever. I would probably need to give you a conversion factor, so I'd probably give you the bars to atmospheres conversion factor. Okay. It turns out that 1.000 atmospheres is 1.013 bar. Okay. They're almost exactly the same, but enough to make a nightmare of us having to convert some stuff here. 23.45. Sorry, don't listen to me. 23.42569 atmospheres. This dude should have four significant figures. Okay. What else we got? We have liters. We're looking for liters. R is just R, so we're good. Now we're going to take PV equals nRT and we're going to solve it for moles. That's always N equals PV over RT. Okay. The pressure we just found out, 23.42569 atmospheres. The volume is 5.66 liters. We were given that number. We're going to divide that thing by R, 0.08258 liter atmospheres over kelvins and moles. and temperature was 316.15 Kelvin. Okay. If we multiply the top, 132.588. I always do it this way with, let me move this a little bit. I always do it this way with the, when we're solving for moles, because sometimes calculators just get confused and it's easier to do it this way and do it in steps so calculators don't get confused. Okay, so multiply the top and we multiply the bottom, 259426. That fraction has units of moles, which turns out to be 5.1108 moles of CO. We're not going to be done, so we're not going to round it, but when I think through it, this should be 3 significant figures thanks to the temperature and the volume. Okay. Now, next thing we need is to take our moles and figure out grams of nickel. Now, this is our stoichiometry part. And we're going to figure out grams of nickel. Okay. When we're doing it this way, when we do P equals nRT first, our start is the moles of gas that we just figured out. So here it's going to be 5.1108 moles of CO, units and a formula for us. We're going to take that, use our equation that says 4 moles of CO will need 1 mole of nickel. Then we'll grab a periodic table and look up the molar mass. Can't say 2 different things at the same time. We'll look up the molar mass of nickel, and that should be 58.69 grams of nickel. Okay. Then we'll multiply and divide these things, and we'll get 74.98851. That's grams of nickel. The moles is 3 significant figures. So 3 significant figures is 75.0 grams of nickel. Okay. Cool, cool, cool. So this is the 2 main ways we have. Either it's going to be stoichiometry first and then PV equals nRT, or PV equals nRT and then stoichiometry. The problem will let you know how that is. Okay. This should say example 3, but I'm not known for paying attention to stuff. So in this example, let's read the some solid terbium-3 sulfite, is reacted with excess HCl. If 0.133 liters of SO2 gas is collected over water at 35 degrees Celsius and 757 torr, how many grams of solid have reacted? Okay, we want to watch out on this one. Okay, this is leading us into something new, and this is this idea of the gas was collected over water. That means we're going to have to do something a little bit extra in our problem. Okay, but let's explain what over water means. Collecting gas over water, this is kind of the setup that we're going to do. Okay, you're doing your reaction. In this example, they're taking potassium perchlorate and manganese 4 oxide and heating it up. This is generating oxygen gas, and the oxygen gas is going to bubble through the tube, come out of the tube, go through this tubing, under the water, and up into this graduated cylinder. This graduated cylinder is full of water, completely filled with water, and is put in the basin before we do this. Okay. The reaction goes, the water goes in, and it pushes, the water goes in, the oxygen goes in, and it pushes the water out. Okay. At the end of the experiment, the gas has been collected. So in here is the gas that came out of our reaction, and the water has been pushed out. The nice thing about this is we can measure the atmospheric pressure in the area that we're doing this, and it tells us what the pressure of the gases that we've collected is. Okay, so the pressure of, I'm just say the pressure of the room or whatever is equal to the pressure of the gas that we collected. Okay. Now, the downside of doing gas over water is the gas we collected is not just the gas we want. In this experiment, our gas collected is the O2 from the reaction, okay? But we bubbled it over water, and so we've ended up trapping water vapor in our oxygen gas, okay? So what we've collected is a mix of gases, okay? And when we have a mix of gases, we're going to have to use Dalton's law of partial pressure, okay? So the pressure that we've collected, the pressure of the gas, is the pressure of O2 that we're looking for plus the pressure of the water that came along with it, okay? This pressure, this water that came along with it, this is known as the vapor pressure of water, okay? It's the partial pressure of water in that mixture of gases, okay? And this is known, and it only depends on the temperature, okay? So what we need to do then is just look up what the vapor pressure of water is at the temperature we did the experiment, okay? This will often be given to us. This is a table from our book that gives us the pressure of water for every 5 degrees Celsius, so we can look up things as we do it, okay? This is typically going to be given, okay? So don't stress about it. Although I suppose if you're working a problem, we could solve for it. I'm not going to worry about trying to do that with us right now. But just maybe think about that as we're doing some stuff. Okay. Let's see. So let's go back to our problem. All right. So since we're doing this over water, this is our red flag here. We want to look for this flag in problems collected over water. Okay, all that means in terms of doing the problem is we have to adjust for the pressure of water. Okay, now let's look at the problem the rest of the way and figure out what else we have to do as we do this. Okay, how many grams? Oh, this is our answer then. How many grams of solid reacted? That's our answer. Our answer is solid. So this means that stoichiometry is second. Okay, so it really means the first thing we're doing is PV equals nRT to figure out moles of SO2. Okay, we're given liters of SO2, temperature, pressure, and we can figure this out. Remember, no, we're doing this over water, so this pressure is water plus SO2. So we have to adjust that. So the first thing we're going to do is tackle this gas part. Okay, so the first part is PV equals nRT, and we want moles of SO2, and we're going to get rid of this pressure issue at the start. So if the P total, what we measured, is both gases, and we know P water, right? Here's our vapor pressure of water, then PSO2 that we want is the total that we measured, 757 torr, minus the water pressure that's in there, 92.7 torr. Okay. Where's my, there it is. Okay, so this means the pressure that we have here is 664.3 torr. This is the partial pressure of SO2 that we need to be calculating with. Okay, this has 3 significant figures. The other thing we have to work through here is the temperature again, which is 35 Celsius plus 273.15, which turns out to be 308.15 Kelvin. Go away, this thing. Go away. Okay. 3. Okay. And this will have 3 significant figures as well because the 35 was a whole number. All right, now we can do PV equals nRT. We're solving for moles, so we'll do that. N equals PV over RT. and we've got this. We feel like we've done this a million times. I hope so, because we need to practice. This will be good for us. Torr, volume 0.133 liters. That was given to us in the problem. The R here, we're using torr, so this is 62.37 liter torr, kelvins, moles. And then the temperature we're doing is 308.15 Kelvin. Okay. When we multiply the top, 204,704.05, we multiply the bottom, 19219.32. This is moles. Okay. And when we divide them, that's 1.065095 moles of SO2 with 3 significant figures. Okay. Now we're going to go through and do the stoichiometry part. In the stoichiometry part, we're taking our moles and we're solving for grams of solids. So we want grams of terbium 3 sulfite. Okay. And we're going to start with the moles of SO2 that we found. So 1.065095 moles of SO2. Okay. Our equation tells us we'll get 3 moles of SO2 for every 1 mole of terbium. It's hard to say 3 and 2 and write the wrong number, the different number. There we go. Terbium 3 sulfite, and 1 mole of the terbium guy, Tb2SO3 3, will give us 55807 grams Tb2SO3 3. This was given to us up there. Okay. And now we'll do our math machines and say 198.133 grams. And for 3 significant figures, this is 198 grams of Tb2SO3 3. Wham bam. Okay. Hopefully this makes sense. Trust in the problem, read the problem, and figure it out. Hopefully we can get there. Okay. Remember, overwater is a big red flag, and we have to adjust the pressure when we see it. Okay. I'll catch you next time.